This is Team 4's Senior Design 2 presentation. Our project is called Lazy Latte Art. Our goal for this project was to create an automated latte art machine that can complete up to 3 different designs with 1 cup of espresso and 1 cup of steamed milk. We came up for the idea for this project when we initially met as a group at a local coffee shop. We had a desire to combine our software and hardware skills with a creative project idea. The goals for this project were to create an automated machine that can complete 3 latte art designs, incorporate our knowledge of Python, Raspberry Pi, and motor control into our project. Today we're delivering in our project 2 distinct latte art designs, an efficient and sturdy physical system, and a GUI for customers to place their latte orders. This is our block diagram, which shows how each of the hardware components are connected together and work together. We have a laptop and monitor connected to our Raspberry Pi, which is connected to 2 servo motors and 2 linear actuators. Each servo motor is connected to a cup, one for the coffee and one for the steamed milk. These can tilt the cups at different angles as the milk is being poured into the coffee. The vertical linear actuator moves the milk cup up and down, and the horizontal linear actuator moves it across with drawer sliders to help perform the latte art designs.
As mentioned before, there are 2 linear actuators, one for horizontal movement and one for vertical movement. They can move between 3 and 4 inches. The espresso cup servo can rotate 0 to 45 degrees, and the milk cup servo can rotate 0 to 150 degrees. We are also using a Raspberry Pi 4 and a motor driver for the actuators. Here is our design implementation. We have the Raspberry Pi on the left side connected to the motor driver. We have 2 linear actuators and 2 servos behind the 2 cups that were 3D printed. The power supply we are using is 12 volts for the linear actuators and 5 volts for the servos. Here is our final implementation. We have protection for all of our electronic components, as well as a bucket under the cups to catch any liquid that spills.
Now to speak on some of the software design requirements, we wanted the rotation of the servos to be inputted as an angle rather than from -1 to 1, and we wanted the movement of the actuators to be put in as a distance rather than as a period of time. All the actuators and servos can run simultaneously, and each latte design has its own class that implements the movements of those functions. So here is our flowchart control for our components. With this, it has an initial position and it gets a signal from the GUI to start. With this, the code tells which servos and which actuators need to move at certain times, and then at the end, it returns them to their initial position. So this is how all the components will move. For the setup of these components, we use 2 different libraries. For the servos, we used PyGPIO because that uses a hardware pulse width modulation. And so these are the pins that we set up for that. And then for the actuators, we use GPIO 0, which is a basic library to set up those. So for each of the components, we create a function in order to call within the classes. For the servo function, we took the angle, or we would get an angle as an input and a pin. This would tell us which servo we wanted to turn and how far we wanted to turn it. The class has it going from -1 to 1, so we had to do conversions to change it from the angle that we were given to those degrees. For the other class, which is for moving the actuator, we were given, we would run to take in a length and to let us know which actuator we wanted to move. For this, it's done based on time, and the time that it took for actuator 1 to move up versus down and actuator 2 to move up versus down was different, so we would need to take those times into consideration when deciding the movement.
This is the code for the main pouring function, which is responsible for the design pouring. This function takes in the pattern number as an input. When the function begins, all 4 components are initialized to ensure that they are at the correct starting position. The initialization runs as 4 separate threads. After all 4 threads start, the threading calls the join function, so all the threads will finish before the rest of the function continues. Threading is used so all the components can run at the same time. Once initialization is finished, the corresponding design class is inputted based on the pattern number. Once the design class is set up, 4 threads corresponding to each component are created. Those threads are then called to start and then the join function is called, so all threads finish before the function returns. This is the GUI flowchart. So the GUI contains two screens, the main menu and a loading screen. The main menu has 4 buttons, and 2 of the buttons are the design buttons. Depending on which button is selected, that is the design type. If no button is selected, the default is design 1. When the start button is pressed, the screen switches to the loading screen until the hardware for the pouring is finished. Once it finishes, it returns back to the main screen, and this goes on until the exit button is called. This is our pouring screen, this is our main screen and the loading screen. And this is a video of the GUI running.
So we decided to implement a hardware PWM using the PyGPIO library. This allowed the servo motors to move smoothly without twitching, as the software PWM got higher level interrupts from the operating system that made the servos twitch. We used 4 distinct threads for the physical objects, the 2 servos and the 2 actuators. The cup for coffee had 1 rotational axis of movement, and the cup for milk had 3 total axes of movement, 1 for rotational and 2 for linear. The GUI used the Kivi library to allow for the user interface. The GUI had a simple design consisting of 2 screens, the main screen and the loading screen. Switching between these screens allowed the user to understand where the process is. The servo motors operated smoothly with the hardware PWMs. We were able to design 2 Latte arts repeatedly, the heart and the snowman, using the linear actuators and the servos, and manipulating their motion, and the pauses between actions allowed us to pour the Latte art designs. This is the progression of the heart design. As you can see on the left, it started off very poor, and as you move towards the right, you get a distinct heart design. This is a video of us pouring that heart design.
And this is the progression for the snowman design. Again, left to right, you can see the drastic improvements we've made. And this is a video of the snowman being poured. We experienced several different challenges during the semester. The primary one was the servo motors were twitching, and we solved this using the hardware PWM mentioned earlier. Pouring latte heart by hand is already a difficult process, so we really wanted to challenge ourselves to create a machine that can do it consistently. The pull-through motion for several designs was the most difficult procedure to achieve, and the milk type and consistency we learned is just as crucial to repeat a successful latte art. If we were to continue this project, we would add an additional axis of rotation, which would allow us to get more difficult designs instead of just a heart and a snowman. We could also incorporate computer vision in order to create custom designs instead of preset designs. We would also aim for a quieter machine with more aesthetic components, and as well as use more sophisticated hardware to better fine-tune our speed and angles. To conclude, this project is to create an automated latte art machine. Building the initial structure went smoothly. However, pouring the latte art designs was more difficult than we anticipated. One successful run does not mean it is repeatable, and we had to continuously do trial and error. And we expected the precision of the motors to be crucial, but milk consistency and temperature mattered just as much. And these are our references.